we have the last, second session for today. It's a little bit. Wait, let me remove this so you will have a little bit more of screen. That's it. It has a little less slides, but there are two numerical notebooks that we're going to go through just to get an idea what are we doing. So to pick up where we left. So the thing that what should remain in your mind is that we have the tools that we are using, like impedance spectroscopy and stuff like that, is valid only for linear, stable, and causal systems. So stable and causal, we saw that it doesn't make any problems for us. We can be pretty sure that our fuel cell is such a system. A linearity is an issue. And we can break linearity either by putting the system in a strange set point on the IV curve, or as I showed you in my case, due to some external factors, like in my case, it was it was the data acquisition system. So in order to check this, I've shown you that you can use the Kramer-Kronig relations. It doesn't matter what kind of implementation you use. I showed here Z-hit. If you have other implementation, you can use it. But be sure to, the message that I would like to convey to you is, be sure to validate your impedance data before doing any further analysis. In such a way, you will be sure that you haven't break the linear condition. So now what are we going to focus in this second part of today's lecture is the issues that arise due to the fact that electrochemical systems are fractional order systems. So let's see what is the problem. There is one particular niche in system engineering, in system identification theory. It's called structural identification. So the question is, what is the order of the differential equation that governs the system? But we are talking now, currently we are talking of integer order differential equations. So first, second, third, nth order, they're integer. And luckily for us, for those kind of systems, there is currently state-of-the-art identification algorithm. It's called subspace identification, or one variation of it, it's called N4SID. The problem is that for fractional order systems, we do not have such a tool. This might seem a little bit strange. So let's discuss in more detail what does it mean. So what we had is previously with on this side with our pendulum, this mass spring damper example, we knew that there is this is the governing differential equation, and it is of second order. But if we assume that we do not know the system, which in practical reasons is always, we have to assume a transfer function that accommodates a quite complex system. So it has p poles and q zeros. And this is quite a complex way. So our question is, based on the observed signals, what is the most probable value of this P? Because we know from system theory, maybe it's strange for you, this is like an ad hoc information that Q must be always less than P. So the question is, can we somehow reliably determine what is the most probable value of P? I'm not going to go into any mathematics. Don't worry. The idea is the following. This structural identification algorithm, what it actually does. It takes linear and time invariant systems, which means that the system doesn't change over time. And we have, so I'm going to draw it here. We have a system. We put input of a system, let's say x over t, and we get its output y over t. And using these two signals in time domain, we can go through this block diagram here, which is implemented. You can find it even Python, MATLAB, whatever. The result would be something like this. It will be a graph showing that if we are using two poles, the eigenvalues are sufficiently high. If we start using higher order poles, we are not gaining any new information. This does not prevent us to say that we're going to use 20 order differential equation, but this says that anything above 2 is an overkill. So the data that you have observed can be accommodated just with two poles. So when you start, what does this mean? So for example, you can use this algorithm and assume that we don't need fractional order systems. You can take an ice curve, but you need time domain data. We'll come to that. And put it through, and it will give you less number of poles than your theory holds. For example, the theory says that we have 5 diffusion processes inside, so we expect 5 time constants, but this algorithm will give 2 or 3. So is our assumption wrong, or is the algorithm wrong? So what you have to understand here is that this analysis is done using only the observed data. This means that it can happen that 2 time constants overlap and that they're undistinguishable. Maybe some of the time constants is buried in noise and it cannot be distinguished by noise, or maybe the time constant is above the sampling frequency that you took. What this algorithm says is, based on your observed data, we can reliably distinguish only 2 poles. And this is really easy. So this means that if I take my data from the pendulum, I just push it up and down with this noise signal, measure x of t and y of t, put it in this algorithm, and this algorithm will result that it is second order equation. So I immediately know the model and I can fit it. I do not need to think what kind of model should I use. That is structural identification. Sadly, this paper here proves that this algorithm is not applicable for fractional order systems. And sadly, even more, we still do not have a tool that can perform such an analysis if we know that the system is fractional order. So current state of affairs is such, even though that we can excite and check the response of our solid oxide fuel cell or whatever electrochemical system you have, there is no way currently to firmly detect how complex our system is. So we are currently in the dark. On day 5, I'm going to show you one approach, how to do it. What we are using regularly is something called distribution of relaxation time. As I said previously, every peak in the DRT curve corresponds to one time constant, and each time constant corresponds to the order of the system. So the number of peaks corresponds to the model complexity. So let's go from here. Why do we have? So the problem is, what we have is, in the literature, we usually have, like on the right-hand side, a vast assortment of equivalent circuit models. And somehow you have to decide which one to use. And the number of these elements Each of these elements is its own time constant. The number of these elements is the complexity of the system. And one would assume that if we have, I don't know, here 5 elements, we should see like 5 loops. It doesn't necessarily mean so. The loops can overlap. So we can have one loop here and one loop here. And when they sum up, they result in this one. So by just eyeballing the ice curve, you cannot distinguish how many poles do I need. And this is the biggest problem what we are facing in fractional order systems. If someone solves this, the ice field will be closed as is for integer order systems. We'll just measure the signals, put it in the algorithm, it will say that there are 4 time constants. This means that our DRT must have 4 peaks, and we can just choose 4 RQ elements and fit it. That's it. No questions asked. We will have a tool like this. Sadly, we do not have it. So we have to somehow work around this. Let's see what's the problem with this fractional order. Where does it come from? So in system theory, these systems are called systems with distributed parameters. It is a mouthful, but what does it say? It is, if we see it in a dimensionality case, these systems are infinite dimensional. What in practical sense does this mean? It says that the system, if we have a diffusion, the diffusion constant is not equivalent everywhere. So the output of a system, it depends on the location where we measure it and the time, because the concentration of a certain reactant is changing throughout the, I don't know, the electrolyte or whatever medium you have, over its dimensions and over time. And this means that each particular segment of our electrolyte has its own diffusion constant. So the diffusion constant is distributed. It's not a single number. It's not a fixed law. It's far more complicated than that. And this is where the distributed parameter systems comes from. So the question is, we know that our systems are infinite dimensional, but on the other hand, we really would like to draw equivalent circuit models. And these are called lumped systems because we lump several these localized parameters together in one RQ element, second RQ element, and so on and so on. So the question is, under which conditions can we apply this thing? We have a distributed parameter system that is fractional order. When can we use equivalent circuit models? So, okay. So, the figure above is something called a transmission line model. It is quite established in the field of battery analysis, and it shows this concept in a really nice schematic way. We can see that there are a lot of localized RC elements that determine how the diffusion in the electrolyte of the battery actually goes over the dimensions of a battery. So what I was saying is that this diffusion constant is not equivalent everywhere, it's not uniform. So localized patterns influence how our reactant moves. And to be happy, we can, so this slide is a rather abusive of notation, of mathematics, of everything. There is a link above where this is clearly described. What I would like to convey with this slide, so check this if you want details. This is a lecture on its own merit. What is the takeaway note is the following. If we have an infinite dimensional system that is linear, and we have some boundary measurements, like in the fuel cell, we have measurement at the end of the anode or the cathode or wherever we measure. It's a finite boundary effect. We can safely approximate this infinite dimensional system with a fractional order lumped model. This means that this allows us to use it as an equivalent circuit model. So why is this important? Well, this is important that here we are, electrochemical systems where chemical species and fluxes are distributed in space, which is what we have, and is a class of systems where we can do this approximation. So what I did now is we have formally a system with distributed parameters. Luckily for us, it is in a special group where we can use it as a lumped model. This means that the equivalent circuit models that we are all using are legal. They are approximation, but they are legal. We can use it. So that was the digression. This doesn't help anything. We still don't know. We don't have a tool to distinguish how many of these lumped models we can use, but it is legal to use them. So now the next hurdle. What can we do to determine how many components should we use? DRT, or distribution of relaxation time, is one of the approaches where you can analyze an impedance curve and somehow determine how many time constants are in there. It was firstly published in this paper. Year of publication is 1941. You can open it, it's freely available. The notation is rather archaic. The authors are chemists with some background knowledge in system engineering, but the notation of system engineering is so hard that it took us a while to decode it. The bottom line is the following. I'm not going through all of this derivation. There are two things what I would like to point out. This relation. So it says, if we have a transfer function, or in our case, this is impedance, this is a complex function, we can divide it as in its real part. So this is real of G over S minus J imaginary part. This is the imaginary part of G over S. And the DRT, the distribution of relaxation time, is defined by this. So it says, take the imaginary part of the impedance, and instead of J omega, put this. And you will get the DRT in closed mathematical form. There is no regularization, no parameter estimation. It's in closed form. So, but we don't, if we knew the transfer function beforehand, we don't need anything of this. We already know the transfer function. We know how many time constants it has. So this is useless. We don't know it. But we have this transformation. So how can we use it? So let's see what is happening. What we have is the impedance that we are getting from their paper, this relation comes out, is we have this is the ice that we measured. This part here is R infinity. And this part here is actually this integral. At this moment, let us assume that we do not have any inductivities. We can safely put here J omega L if we need it, but let's not complicate stuff. What is the problem with this? The problem with this is this integral equation doesn't specify the shape of g of tau. Just to give you a gist, so a g of tau, we are usually to see it something like this. 2 or 3 or more ridges, we integrate out and we get the ice curve. But the same thing can be obtained even with this function. Because when we integrate these peaks, it will give the same area as this above. So we can think of numerous ways numerous candidates for g of tau that are distribution of relaxation times. It's an ill-posed problem. There is not a single solution. But we would like to see something like this. And because we would like to see it, we have to somehow force the solution to look like that. So there are two things that we need to discuss here, is that we can, from the distribution of relaxation time, we can determine this point here at omega 0 using this relation or this relation. So just integrating throughout the whole area of the DRT, we are getting the polarization resistance. So now I'm going to provide you a tool how you can do it, first numerically, then from a measured signals. Oh, come on. Okay. So I'm going to jump, actually, this is 2 slides here, but I'm going to jump directly on the note. It's easier so that you can see it, and I'm going to comment on the fly. So let us, the idea is the following. There is a library in Python that allows symbolic manipulation. You can have it in Mathematica, Wolfram Mathematica, Wolfram Alpha, in MATLAB, wherever. So let's do DRT analysis using this thing. So what I did now, I just include all these libraries that are required, and I would like to find out what is the DRT of the impedance that looks like this. I came up with this equation just for the sake of demonstration. It is a 2 RQ elements with a series resistor. We will get to it. So let's define it. This is my model, and what I have to do is I have to take the imaginary part of my impedance. This is H, and change it. Instead of J omega, put this S minus JP half. Nothing, just change of variables, nothing special. I can start doing it by hand, but I can ask Python to do it instead. So what I do here is I said, take the imaginary part of my impedance and substitute omega with T minus J pi half plus, and again, the second part, minus T plus J pi 2. And then print me the DRT. I can do it here. And this is the relation of the DRT in closed form. There is one minor issue here. This library doesn't know how to calculate imaginary of -1 to power of alpha. We know that it is -a to power of alpha is aj pi alpha. So let's force this substitution here also. Nothing special. This is the closed form of DRT curve. What does this mean? When you take a paper, published paper, and they measured an ice curve. Fine, you have to measure it. And then they decided to fit an equivalent circuit model. Fine, they fitted it. And then they used a DRT library to calculate the DRT from the impedance curve. That is not needed anymore. Either you decide to make the equivalent circuit model and the DRT pops up in closed form, or you immediately jump to DRT. There is no additional information. DRT is just algebraic manipulation of the transfer function. And you will see a lot of papers that do DRT analysis where they say the DRT curve for, I don't know, RQ elements or for some strange impedance curve was derived by this and this author, and they cite it. Yes, it is a painful way to derive it, but having symbolic libraries, you can just go here, change this relation to whatever impedance you think of, make it as complex as possible, and go down through this, and you will get a really big sausage, and this will be the DRT in closed form. I guess someone can reduce this equation furthermore, but if we plot it, and I'm going to plot it, this is the DRT in closed form. That's it. So let's go backwards now. Let's say that I have the DRT, and I want to calculate this. I know the serial resistance. I will integrate this, and I should get the impedance back. If I integrate from 0 to infinity, I should get the polarization resistance, and so on. So let's do it. I put some random values just for the sake of the demo, and let's see what will happen. So if I plot, I'm going to explain what is happening here. So I take the DRT function that I calculated here, this DRT, and I put those values inside, and I said here, please plot me this DRT value. And here it is. It has two peaks because I have two RQ elements on the same frequency where they should be. Everything is it should. There is no regularization. I'm doing symbolic analysis. So I derive the DRT in closed form. Why I'm saying this? If you in your research at one point jump from impedance measurement to an equivalent circuit model, you make a decision how complex your model is, the DRT is free. You don't need to do anything. You can have it in a closed form. All you have to do is put the model here, run this, and you will get the DRT. That's it, 100%. If you want a different DRT, you have to change the model. And there are even more bizarre cases where a person published have a measurement of impedance. It's okay, the measurements are okay, valid. Assumed equivalent circuit model of 3 RQ elements, and then draw a DRT with 5 peaks. One of those results is false. I'm not saying which one, but one is false, because equivalent circuit model is the model of the impedance, and the DRT are one-to-one. There is no extra information. DRT is just a transformed impedance. Nothing new comes out of it. It's more visually pleasing. We can see the peaks, undoubtedly. For us, it's easy, but the amount of information that is present in this plot is equivalent to the information present in the ice curve. So let's go back now. We have this in closed form, or let's say that we have this in a numerical like this plot. Let's go back to our impedance. We can do it. All we have to do is integrate this, actually solve this integral. Where is this? Sorry for jumping up and down. Solving this integral. But we are going to solve it numerically. I'm not going to solve it. We can do it symbolically, but let's do it in a numerical way because you will have only data. So what I'm going to do here is take the data and integrate it with trapezoid integration. I'm not even complicating with more sophisticated numerical integration. Simple trapezoid integration. I integrate it, and I get that the polarization curve, polarization resistance is 0.0748, and the actual is 0.75. So I made, I don't know, 0.1% mistake just by choosing the most basic integration stuff. So I can do this. Can I go all the way back to my impedance? I can. So I will take this G and I will integrate it over it. I cannot go from 0 to infinity because I have only from 10 to the minus 1 to 10 to the 5. And I can assume that outside of this region, this value is 0. So I can just cut the integration out. And what I do is simple trapezoid, and then I divide it by this down. 1 plus JW tau. 1 plus JW tau. And I integrate it, plot it. So the blue line, which is not visible, is the theoretical impedance. The orange one is obtained by numerically integrating the DRT. So what I'm saying here is, if you selected equivalent circuit model, don't do DRT. They are exactly the same thing. And when you can use, on the other hand, you can use the DRT to see how many peaks are visible, 3, 4, 5, 6, whatever, and then select appropriate model with that amount of RQ elements and fit that. So the number of peaks in the DRT must be the same with the number of time constants in your equivalent circuit model. That must be spot on. Otherwise, you did a wrong selection somewhere. I'm not saying where, but they must be spot on. That's the thing. So what I showed here is how you can do it symbolically. But we don't, if we knew the model, I wouldn't be standing here. We don't know the model. We cannot do this. We can do this only for known equivalent circuit models. Let's do it only for measured impedance curves. Let's go back to the presentation and continue from there. So, we covered this. This is the link to the note that I set here. So, what we have now is one of the most widely used algorithms for calculating DRTs numerically. So you have a measured impedance values. We don't know the equivalent circuit model. We don't know this. And we would like to transform these impedance into these DRT curves without any assumption of a model. The most commonly used algorithm is algorithm developed by Francesco Ciucci. He was a professor at Hong Kong University. He's now in Germany. His algorithm is freely available on this link. The paper down is the one where it describes it. I urge you to try it. It's really robust. What it does is the following. As we already discussed, this value here is not a single one. There are multiple G functions that solve this integral. What he assumes is, he says that for every point that I've measured, I assume that there should be a peak. So he assumes that there is a peak everywhere. And then he tries to infer which of these peaks should go back to 0. So should go back to 0, and which of these peaks should go up. And then sum all these things together. So how he does it? He assumes that each time constant is not a peak like this, but rather a kernel. It's a head function. And you will, when you open it, you will see that you have a choice of like a Gaussian head, a skewed head, and a lot of different choices. And what he does is he puts a lot of these heads. He puts, then when the optimization goes, some of these values go back to 0, some of these values go back up, and when it sums it up, you will get a head like this, and a head like this, and a head like this, and when you sum it all together, it will come something like that. That is his algorithm in a nutshell. There is one particularly important thing here, and this is the value of lambda. It's called a regularization parameter. And what does it says? It says it penalizes a solution that has a lot of spurious peaks, because we would like to have a DRT curve like this and not DRT curve like this. Although maybe this corresponds to this. We would like to have smooth curves. And that's why you have to choose this value lambda. So let's see how this value affects and how you should read the DRT results in the papers. This is really, really, really tricky. So let's try this. Again, I'm going to go back to my ice curve that had this strange value here. And I'm not going to correct it. I'm going to say, yeah, it looks great, although I previously showed that this part here is non-linear because of our data acquisition mistake. But I'm going to say, yes, this is a nice inductivity region. Everything is nice. Let's go for it. Fine. So our measurements are quite dense. So in order not to lose too much time, I take every second note of a measurement, and I take only the negative value of the impedance, not to play with the inductivity. You can do it just for the sake of demonstration. So I have these red points here, and from these red points, I would like to calculate a DRT curve. So let's do it. When we try this algorithm for DRT, we have to choose the value of lambda. And you don't know the value of lambda up front. You have to decide, do I want to penalize it a lot or leave it to have a lot of peaks around? So when you run this algorithm that will generate a lot of curves, it will run for around 5 minutes. So we won't wait it for 5 minutes here. I already pre-calculated everything and upload everything on the GitHub. So we can just open the pre-calculated values and plot them. So what we see here, we see that for different values of lambda, we are getting different DRT curves. If you see the black ones behind, they show only one very white peak. Then as we decrease lambda, this very white peak divides into 2 peaks. And now the question is, do we have 1 time constant, 2 time constants? And if I start decreasing this lambda furthermore, several new will appear. Which one is the proper value? Usually, when you see results like this, results are presented in the papers in this form. This is the final. They've selected 1 lambda. Most probably, they've selected the default one that is in the algorithm, and no one reports it. And they say, okay, we saw 5 peaks. Or if they were wanting to see 5 peaks, they tune this lambda so that 5 peaks occurred. And it's there, and nobody reports this alpha. But now we know, because I showed you previously, that if I take this curve and if I integrate it, I can look back at my ice. So what we can do is, let's integrate these curves. And let's see the polarization value first. And this is really fast. It seems that it jumps, but take a look at the y-axis. So more or less polarization curve is constant. Polarization resistance is constant. This is logical because more or less the area under each of these DRT curves is constant. So this says that polarization resistance is not that dependent on lambda, which is logical. Let's go one step further. Let's calculate the ice curves. So the dotted line is the originally measured ice. All the other lines are ice curves obtained from the calculated DRT. So what I did is I started from the dotted lines, generated a lot of DRTs with different parameters, and from these DRTs I wanted to go back, and I was unable. So more or less, one can say that none of those DRT curves closely represent the ice results. This is logical, particularly in this high frequency region, because that is the place where my Kramer-Kronig failed. Doesn't matter at the moment. This feedback is never reported. And when you do your own analysis, you use tools and put some parameters there or use default parameters. You can always do this feedback check and see whether my DRT actually corresponds to the measured ice. In some bizarre scenarios, it can happen that the algorithm for DRT converges somewhere, but it is far from the measured ice. It is the best what the algorithm could have done, but it's far, far from the measured ice. So the DRT, what you are looking, is an artifact. You should not take it as a result. So the check are just these 3 lines of code, regardless of the methodology that you use to calculate the DRT. These 3 lines can be used. So these 3 lines are doing nothing but integrating out this. Simple. So when you start doing experiments, most probably you will have multiple ice curves. You do measurements over time. You will take the first ice and you will calculate a DRT. You've selected some parameters for DRT. Fine, they work. Freeze them and don't change them until the end of the experiment. Because what you can do is you can start in the beginning and then you say, in the next ice, I will tweak a little bit this, tweak a little bit that. So you're practically changing your instrument on every measurement. Keep it fixed. That is the message. And there is even better approach than this. Let's go back to the presentation. There is a better approach than this. Again, so we are going back to something that Francesco Ciucci did, and then one of my students actually upgraded quite a bit. We even got a mail from Ciucci saying that he did a good job. So let's discuss this. This is something what is published by Ciucci and called deep DRT. If you Google this, you will get this approach. So what's the idea? We know that we are looking for this curve. We don't know its structure. So what can we do? we can use a general approximation. What is the best general approximation? Some sort of neural network. Okay, so we say, let's take our ICE results and calculate the DRT. But we don't know the true DRT. How can we train the neural network? So when this finishes, we do the integration, these 3 lines of code that I show you, and the result here is ICE estimated. And then we compare this with this. And in such a way, one can train the neural network. So let's see this result. The frequencies that are usually entered here as an input are logarithmically spaced. So usually someone does this kind of change of variables. And now, from this point onwards, I'm going to go through some derivations. The result will be a rather huge integral. And I'm going to retype that in Python to see how simple it is. So whenever you see those kind of integrals, don't feel alarmed, just type them out. You can solve them numerically. No one asks you to solve this symbolically. Okay, let's try to solve this. So we would like to separate this part to the real and imaginary components. And we can separate this into this way, and this is its real part, and this is its imaginary part. You can do it by hand, or you can use some symbolic derivation toolbox. This is simple arithmetics, nothing special. Okay, so we have this. Then we do change of variable. These are the changes of variable we do, and the original integrals are becoming this. This is the real part, and this is the imaginary part. So this we put here, and this part we then split into real and into imaginary. This is the real, this is the imaginary. I'm not going through a derivation. I have it symbolically in the notebook. I'm going to show it to you. So what we have now, what we obtained the following thing. I'm going to scribble it down here. So this is our approximation of the function g of tau. This is our DRT. And from this DRT, we split, something broke. So again, this is the DRT. And then we split it into real part and imaginary part. We can do it. And then integrate this out. And we have real, this is the imaginary ICE, and this is the real ICE. And then we can compare this with the measured one, and in such a way, we can do the training. So all we have to do is the following. We have to define a certain neural network and integrate this neural network using these 2 integrals. These 2 integrals are rather complicated, but let's divide them by parts. So what we have, this part here, this gamma is our neural network, and it comes here. And then this part here is this complete integral. So we have the denominator is 1 over jxy to the power of 2. So this is the part here. And this whole part is this one here. Again, I can go through the details. And this is all you have to do to calculate this DRT. So the result is the following. The result is the red line. So we got 2 peaks. The true one is the blue one. We can see that we have here a lot of spurious spikes concentrated at the proper locations. So what we have to do now is somehow tell the algorithm that we don't want these spurious spikes, but we want stuff to be smooth. How can we smooth this thing out? By penalizing the second order derivative. We will say, take this function, calculate the second order derivative over whatever it is, and minimize it. If the second order derivative is low, this means that there are no wiggles. It will become a smooth line. Simple as that. Let's implement this. You can ask ChatGPT or open Wikipedia and ask simplest way for calculating second order derivative, and this is the result. It is Euler's rule for second order derivative. Is not Runge-Kutta, is nothing special. Second order Euler. You can type it out. Actually, you don't even have to type it out. You can just take this to ChatGPT and it will type this out. This is actually Gen AI code. Okay, and we put that inside, and then we get the blue line behind. So let's check now how all of this works. Again. And there are several peculiar things that I'm going to talk about now. So again, I'm loading here a data from an experiment that we are going to use quite a lot throughout this workshop. It is an experiment of 600 ice curves measured over a period of 3,000 hours of a degrading solid oxide electrolyzer. And we have these 600 ice curves already calculated. I will plot some of them. So I choose background. Wait, let me see where I have it. Then I'll go back. The ice curves are really low, right? Okay, let's go slowly. So because I'm going to train neural network, it is rather slow if you don't have a GPU. So this part here just checks what kind of GPU you have. If you don't have a GPU, it will just print a warning that it is a CPU and it will take some time, but the code will work. What is the goal of this thing here? Let me write this down. Scribbled it. Wait, I'm going to do it like this. So I'll have a whiteboard. So what we have is, we have a map of 600 DRT curves. So we have 600 ice curves. And each ice curve was calculated at 210 frequency points. What can I do is, actually, if I use Chuchi's algorithm, I can take this ice curve and calculate a DRT, take the second and calculate DRT, and so on, by taking into account that I always keep the same parameters, lambda, all over the place. In such a way, I can guarantee that I'm using the same instrument for each and every measurement. If we take a neural network approach, so the same data set, 600, 210, and we take this one and train our neural network and get the DRT. Then what Chuchi does, takes another one, trains a new neural network and gets another DRT. That is his approach. What is the problem here is that each neural network learns a little bit different. So in essence, it will be as if the first neural network uses parameter lambda 1, the second one uses lambda 2, but it's hidden from you. And this is somehow obscured. What I'm presenting here is we take all 600 ice curves, each with 210 points, and learn all DRT curves at once. So one neural network learns 600 DRT curves from the get-go, the whole experiment. And the bizarre thing is you don't even have to put this as an input. You can put noise as an input. And because we are integrating this DRT back to the ice, the neural network will learn how to generate ice through noise. So it will bootstrap itself. It's ultra bizarre. Actually, the same algorithm is used in a generative AI for generating images. It's a diffusion model. It starts from noise. And because we are integrating real and imaginary parts separately, we are guaranteed that the resulting ice will adhere to Kramer-Kronin's tests. So in the same fly, we can generate DRT curves and check Kramer-Kronig for every ice in our experiment with one kick. So let's do it, just to see how fast this is. Now I'm going to do 600 ice curves on the fly here on my laptop. This is the function that implements these two integration, the real, the imaginary, and the real, the one that I showed you previously, the overall trapezoidal integration, and so on and so on. It was already there. A small module that will estimate the serial resistance. I'm going to draw this out just to get an idea. And let's do it. Okay, here is the training. So now I'm training 600 ice curves without any polishing, without any regularization. Currently, this is currently running on my laptop. So it will take like 40 seconds. So in 40 seconds, we are going to do 600 DRT curves and 600 Kramer-Kronig tests all in once. And then this will repeat itself one more time with regularization stuff. And then we're going to see the results. All right, this one's done. Now the next one. So it took 50 seconds. And my laptop is a rather old one, so nothing special. So there are now several questions popping up. Why 4,000 iterations? Why no 4 million iterations? And then this will last 10,000 times more or whatever. We're going to see the losses now and going to discuss what this means. So it's done. These are the losses. And we see that they converged. They decreased somewhat. Maybe we can go a little bit further, but they stabilized quite a lot. The blue one is the one with regularization, without regularization. So we allow to have more peaks. So the DRT can adopt more closely to the ice curve. The red one is the one that we want it to be smooth. And because we want it to be smooth, and we know that we have imperfect ice, the error is a little bit higher. But nonetheless, let's plot the results of the first 10 ice curves. So the dotted lines are the measured values. And the solid lines are the ones that were learned by the neural network. And we see that we can easily see where there is a discrepancy. And this is actually 50 Hertz. When we were doing experiment, we didn't isolate the power supply properly. And at 50 Hertz, we had this artifact where Kramer-Kronig failed, but I left it on purpose here so we can see it. We see the issue at high frequency, and we see some issues at the low frequency, which is logical. This is the imaginary, and this is the real part. And we can always draw the DRT curve. And now I'm drawing the first one. We have 600 of them calculated like this. And here they are. So the blue one is the DRT curve with smoothing, and the red one is the DRT curve without smoothing. And one would say, okay, the red one is useless. We don't want to use it. We would like to use the blue one. On Wednesday, I'm going to flip your minds, and I'm going to show you that you don't have to regularize DRTs. Actually, the spiky one is good enough. So what the takeaway note from here, what I would like you to keep in your minds are the following three things. When you do your analysis, because we are dealing with fractional order systems, you make your ice curve and you check it with Kramer-Kronig. This is done. And then you come to a fork in the road. Either you decide on an equivalent circuit model. I don't know how, you will decide somehow. And if you do that, DRT exists in closed form. The other fork is you select any of these algorithms for calculation of DRT and calculate the DRT. You will somehow select lambda parameters, width of the kernels, whatever hyperparameters you have to select. When you select them, calculate the ice back to see that you don't have really strange. The DRT might look okay, but if you integrate it, the resulting ice might be completely bonkers. So integrate back just to validate that the DRT you are looking is logical. And then freeze your parameters and use it the same throughout your experiment. What usually people are doing when you have multiple experiments, you can then, on multiple ice curves, maybe the first run is a run-in phase, heating up the stack, maybe the ice curve is not a proper one, the battery is in first cycle or whatever. Make several initial ice curves and then tune these parameters and fix them and keep them constant throughout the experiment. In such a way, you are not changing your instrument sensitivity. You fixed it and you keep it constant. And for the love of God, report which hyperparameters you used for DRT so that people can recreate. And since we are here, I'm not doing material characterization. As you've seen, I always do experiments that are long run. I always have multiple ice curves. And my task is usually comparing multiple ice curves. What I'm going to show you on Wednesday is that in such a case, you don't need regularization. The spiky thingy is perfect enough because both things have the same information. But if you do material characterization and you would really like to know which time constants are where, then the smooth one is the only one that is helpful. So my job is easier. I'm not a chemist or material engineer. I don't care about material characterization. What I get is job done. I can use it as is. And in those cases, I'm going to show you that the problem is simpler. You don't need regularization at all. This is something that is rather brand new. And this is why we can do it in such a way. So to recap what this last slide was, and with that, I'm going to wrap up today's session. Let me put one more slide and draw it so that you will get an idea what happened altogether. Okay. So what I have is I had 600 ice curves, each with 210 frequencies. I used one neural network that generated 600 DRT curves, calculated in, I don't know how many, I think I calculated them on 6,000 points. So the number of frequencies that I had as input doesn't mean that they should calculate as the output, because the neural network just interpolates everything. Then I integrated this part here, split it in a real and imaginary parts, and I then compared these real and imaginary parts with these real and imaginary parts. And that is how I did the training. But by doing this integration here, I guaranteed that these two pairs are always Kramer-Kronig valid. So in one pass, I took raw DRTs, raw ice curves, put them through this neural network, and because of this integration, I forced the neural network to learn such DRT that will comply with the Kramer-Kronig relations. And the resulting stuff are smooth ice curves that are as close as possible to the measured one and that are in the same time Kramer-Kronig valid. So everything that I was telling you the whole day today is in the last slide, all in one shot.